Waking life is literal. We navigate physical spaces and concrete tasks. Yet during REM sleep, the brain abandons literal replay for highly abstracted, symbolic narratives. Classical psychoanalytic theories interpreted this transformation as a method of masking latent psychological wishes to protect the sleeper. Other classical frameworks analyzed these bizarre narratives as expressions of deep structural archetypes shared across human consciousness. Modern memory consolidation models focus on how dreams integrate recent experiences into existing neural networks. While these models identify the material the sleeping brain processes, they lack a mechanical explanation for the brain's conversion of literal events into complex symbols. The Brain Kinematics Model, or BKM, provides a systems-level framework to address this mechanical gap. In this model, dreams function as dynamic narrative expansions of topological strain structures. A strain structure represents the cognitive load or unresolved tension left behind by a waking experience. By deconstructing two specific clinical case studies, we can map exactly how this cognitive load compresses into a symbol and then unpacks into a narrative. Analyzing dreams through the lens of topological strain resolution allows us to track the specific mechanics of neural load during sleep. Waking experiences generate continuous strain flows across neural pathways, represented by energy pulses. Many flows reach completion when taking physical action. Others remain partially unresolved. The energy halts midway, pooling in the network. We define these unresolved nodes as residual strain traces. These traces remain dormant during the waking day, suspended until the brain enters REM sleep. Once sleep begins, these residual strains reactivate and interact with the brain's sensory and emotional systems. The raw input for a dream is the precise, unresolved structural strain left in the wake of a waking event. We can observe this pipeline in action through the first clinical case study, known as the cow dream. The dreamer reported returning to their parents' home in Iran, which had been renovated, though they noticed crude coal writing remaining on the walls. The central conflict involved keeping a cow inside the home. The dreamer felt intense worry over its care, its costs, and the risk of a corrupt official seizing it during the dreamer's absence. Through symbolic compression, the sleeping brain forces the waking strain into a single, dense image. The cow becomes a carrier for a strain cluster involving stewardship, maintaining a valuable asset that persists during absence, mapping to the dreamer's ongoing intellectual publications and family responsibilities. To process this dense symbol, the brain employs narrative expansion. Since the symbol itself is entirely static, the brain must construct a dynamic story to fully explore its implications. Narrative details, like calculating maintenance costs or worrying about caretakers, represent the brain testing the strain's implications. This dream is a complex topological calculation regarding the cost of maintaining value when the dreamer is unable to provide direct supervision. Because dream narratives often contain extraneous visual noise, we need a method to isolate the originating waking concern. The BKM framework applies the principle of the strain gradient, also known as the emotional center. Meaning is not distributed evenly across a dream. This graph tracks emotional intensity, showing that the true fingerprint of the strain is localized at the point of highest intensity. We can apply this principle to the second case study, the exam dream. The narrative begins with the dreamer realizing they are missing an exam. Throughout this sequence, the emotional intensity remains relatively low and flat. Later, the dreamer discovers children wasting food in a cafeteria, triggering a sudden outburst of anger and a forceful intervention to restore order. Plotting this event reveals it as the dream's emotional climax, marking the highest strain gradient in the narrative. This approach challenges the common interpretation that exam dreams are a direct manifestation of performance anxiety. In systemic terms, an exam is a comparison mechanism that tests an internal model against external reality. Biological systems require periodic checking against external data to prevent their internal models from drifting. The school exam reconceptualizes as a symbol for this intervallic reality check. Failing an exam implies the comparison occurred but yielded a poor result. Missing the exam implies the calibration process never happened. When this calibration is skipped, the brain's internal model loses its reference point, triggering a state of systemic uncertainty. Without a clear external validation signal, the waking mind generates intense feelings of being completely idle or entirely socially unconnected. The exam dream identifies a systemic failure in the brain's calibration with its environment, manifesting as uncertainty when external feedback signals are missing. Waking life typically generates multiple unresolved strains simultaneously. Dreams act as integration systems, where recent events, older memories, and future anticipations merge into a single structure. When evaluating these structures, we can avoid the distraction of peripheral narrative details. Locating the highest strain concentration, the emotional peak or the central image, reveals the unadulterated fingerprint of the waking mind's load. Mapping dreams as dynamic topological resolutions allow us to chart the functional architecture of the sleeping brain.